Okay, so people often say that you can't get something from nothing, but what I'm going to try and demonstrate today is you can pretty much get everything from nothing in a particular kind of sense. So, what I'm going to be doing is playing around with some ideas from set theory and showing how, if you look at the empty set and you do some fairly simple things to it, you can create an immense array of different objects. And I think this is fairly interesting for several reasons. I think it's interesting mathematically because I'm going to be talking about some very interesting patterns that come from elementary objects. And another reason why I think this is fairly interesting is because it has to do with sort of metaphysics. For example, the universe supposedly, according to some people, erupted from a single point in a big bang. So people ask, how can you get something from nothing? Well, it turns out that, in a sense, if you analyze the empty set in a particular way, it actually contains an immense amount of information. And so one can almost see the empty set as a kind of place where a load of differentiated objects can be created. So, without further ado, let me just get down to it. So, I'm going to just recap a few ideas from set theory. So, a set is just a collection of objects, and we usually write a set with curly brackets. So, for example, we might have the set here, which contains the word dog and the word cat, and we denote the beginning and the end of the set with these curly brackets. We can also think about sets of numbers. For example, this is the set which contains the number 1 and the number 2. Okay, so the only slightly advanced concept which I'm going to be talking about today is the idea of a subset, and it's not really that advanced. A subset is just a set which is contained within another set. So, for example, if we think about this set here, we can ask, what are all the subsets of this? Well, 1 is a subset of the set containing 1 and 2. The set containing 2 is another subset of this. The set containing 1 and 2 is another subset of this. We can just define things that way. And there's also another subset of this called the empty set, which we write like this. And so if we put some curly brackets around these things, what we have here is the set of all subsets of the set containing 1 and 2. So this is the kind of thing we're going to think about today. We're going to think about the collections of subsets of sets. Okay, so just to show that the empty set is a very natural concept, which has lots of applications, I want to look at another idea in set theory, which is the idea of the intersection of a pair of sets. So if we have a set A and a set B, then we say that the intersection of A and B, which is usually written like this, is the set of all elements which are members of A and members of B. So, for example, if we have the set 1, 2, and we have the sets 2, 3, then the intersection of those two sets is equal to the set which just contains 2. So we would like to define set theory so that the intersection of any pair of sets is a set. Just like, if you add two numbers together, you always get a number. But we can consider cases where you can see that the empty set is useful for this purpose. For example, what about if we have the set 1, 2 intersected with the set 3? Well, what this says is, in English, this says this is the set of all elements which are in 1, 2, and also in 3. But clearly there are no elements which belong to this set 1, 2 and this set 3 at the same time. So what we write is that this is actually equal to the empty set. In other words, there are no elements which belong to this set and this set. So the intersection of these is the empty set. The empty set basically acts like a kind of zero in set theory. In fact, sometimes it's written like this, which kind of looks like a zero. Anyway, if you think in general about a pair of sets A and B, it makes sense that the intersection of those two sets ought to be a subset of A and a subset of B. And so if you now look at this sort of thing at the bottom here, that kind of implies that the empty set can be considered to be a subset of the set 1, 2, and it can be considered to be a subset of the set 3. And in fact, since there's nothing special about these particular sets really, what we actually have is that the empty set is a subset of every set. In other words, to put it a little bit less precisely, whatever you have contains nothing within it. Okay then, so now we're ready to start our interesting exploration of nothing. So we're going to start with the empty sets. And all we're going to do is think about what are the subsets of the empty set. Well, there's only one subset, and that's the empty set itself. And so the set of all subsets of the empty set is written like this. And so let's just call this, just for the sake of notation, we'll give this a name. We'll call this S0. And let's call this S1. Now, what we're going to do is we're going to look at this and we're going to think about what are all the subsets of this. So, what are all of the subsets of S1? What's the set of all subsets of S1? Well, we'll call that S2. What is it? Well, we've got the whole thing that we started with, and also the empty set, because the empty set is always a subset. And that's it. So we're already starting to see something funny going on, just by starting with nothing, the empty set, and this very simple idea of getting subsets. We're already starting to see these kind of non-elementary mathematical objects appearing. And what I want to talk about is what happens when we carry on this process. What kinds of things do we see when we just keep doing this operation where we get the collection of all subsets. And it turns out that very, very rapidly we get massive amounts of information, and we get some very, very interesting kinds of fractals and self-similarity, and lots of very, very interesting things, I think. And so it can often be quite useful to associate these sets with pictures. I mean, essentially, what we've been dealing with are kind of lists of brackets, you know, curly brackets, left curly brackets, and right curly brackets. But if we draw them as pictures, it's a bit more interesting. So we begin with the empty set, and we could illustrate this as a circle. Now, after we update this, and we take the set of all subsets of it, we get this. And we can illustrate this as a circle, which contains a circle. So here we're using a circle or closed loop to represent a set which encapsulates something else. So when we've got a closed loop encapsulating something A, that means that you know, that kind of represents a set which contains A as an element. So this is the thing we get after one update. If we update this, then the next object we get is the set which contains the empty set, as well as the thing which we had previously. And we can also illustrate this using our pictures. So we'll have a big loop to represent the set itself, and we see that it contains the empty set, which is written as a circle, as well as also containing this thing here, which can be written as a circle containing another circle. So this is a sort of easier to understand way of illustrating these sets, I think. Now, the next thing we get when we take the set of all subsets of this is quite a bit more complicated. And so we write it symbolically like this. It's the set that contains the empty set, and it also contains this kind of empty set within a set. And it also contains this kind of three-layer analog. With three left curly parentheses and three curly right parentheses. And it also contains a copy of what we had before. So we find that in general, on the next iteration, one of the elements in the set we get is equal to the complete collection that we had before. And there we have it. So let's just make a couple of observations here. Firstly, as I just said, we have this element here which is actually equal to the thing which we started with. And this is usually the case when you take the set of all subsets of a set. Well, the set itself is a subset of a set, so obviously it should be within that. Another kind of interesting thing to notice here is that we've got these very kind of simple looking things, which symbolically are basically just so many left parentheses followed by so many right parentheses. And so, like here, we've just got one left bracket and one right bracket. And here we've got two left brackets and two right brackets. And hopefully you can see that as we continue this kind of process of, taking sets of subsets, we get higher and higher depth objects like this. And really, these objects almost directly represent the integers. And so what I'm trying to say here is that amongst the many different objects that we get by doing these kind of operations of just taking subsets, some of these objects are basically equivalent to the integers. So in a way, you can think of the integers as being generated by taking the empty set and doing all of these, looking at subsets kind of operations. Anyway, so this is the thing that we get kind of after the next update, if you like. And let's represent this pictorially so it's a bit easier to understand. So what have we got? This is the empty set. This is a set which contains the empty set. This is a set which contains a set which contains the empty sets. And this is a kind of copy of what we had before. So it's a set, it contains the empty set, and it contains something which contains the empty set. And all of this forms a set, and this is a pictorial representation of this thing above. So here we are. This is the thing we get after our next update. How many elements does this thing have? Well, this set has 1, 2, 3, 4 elements. Okay then, but you can see that it's significantly more complicated than the thing we had last time. So obviously a good question is, what happens when we update this system? What do we get then? Okay, so this is actually the thing we get when we do the next iteration. So when we take the set of all subsets of the thing we were just looking at, we get this really quite complicated object here. This thing has 16 elements, and as you can see by the picture below, it's really a very intricate kind of thing. I mean, it contains the set we were previously looking at, and it really has a very lot of structure to it. And so there's a lot of things to notice here. I mean, one thing to notice is that we're getting these kind of sets, like say this one here, which has 1, 2, 3, 4 left brackets and 4 right brackets. We could think of that as representing the number 4. So we're getting lots and lots of objects appearing which we can use to represent things in mathematics. In particular, we're getting the integers kind of naturally appearing from this conglomeration of things. Another thing to notice is that we have a kind of there's a kind of recursive nature here because the next iteration of this process is going to have an element equal to this set. And another thing to notice, which should be quite obvious by now, is that the number of elements we get as we keep doing this process is growing very rapidly. So you might wonder then, what happens if we look at the set of all subsets of this? How many elements will that have? Well, if you just recap, we started off with the empty set, which obviously has no elements. Then, after one iteration, we had something that had one element. Then we had something with two elements, and then four. And then we had something with 16 elements, which is this. And so, how many elements will we have on the next iteration? Well, it turns out that actually we'll have 65,536 elements within the thing that we get if we take the set of all subsets of this. So that's a really, really big number compared to what we've been looking at before. And in fact, basically the size of these things which we're looking at are growing incredibly rapidly. It's what they call a power tower in number theory. Basically, here we have 16 elements, that's 2 to the power of 2 to the power of 2. If we update this again, then we'll have 2 to the power of 2 to the power of 2 to the power of 2, that's 65,536. And then if we update again, we'll have 2 to the power of 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 2, which is just like an immensely massive number. It's like about 10 to the power of 20,000 or something. It's just unimaginably huge. And so we continue. So what I'm basically just trying to illustrate is that just by getting the empty set, the simplest thing you can think of, the thing that's contained within anything, and just by thinking about its subsets, you see basically a kind of infinite amount of complexity emerging in some sense. And so I just think this is a fairly interesting little observation. And I'm sure that this particular sequence and these particular objects have lots of other properties which are just waiting to be discovered. It should be a fairly interesting line of research. So if we look at this collection of sets in the right way, it can actually look rather beautiful. So for example, we can make a network by thinking of each of these sets here, these members of this massive set, thinking of each of these elements as points, and then we'll link a pair of points when they have an element in common. And so, for example, we would link the point corresponding to this to the point corresponding to this, because they both have this element here in common. And so, if we do this kind of thing, it's actually called forming an intersection graph in graph theory. But if we make such a thing, we find quite a nice way to visualize this structure. And we get this rather nice kind of network here, which we can draw and illustrate in 3 dimensions. Now, as I say, if we iterate this system further, we get a collection of 65,536 elements. And so that would obviously lead to a much larger network. And it would be very pleasant, I imagine, to see what kind of structure that creates. I imagine it would have lots of symmetry and such. And so basically the point I'm trying to get at is just that by looking at even the empty set and some very, very, very elementary mathematical operations, we can see some really beautiful objects appearing.